Good morning. I am Devasena. In this lecture, we are going to discuss about state space analysis and introduction. This topic is present in the subject Control Systems. Introduction to state space analysis. State space analysis is an approach deeply rooted in the techniques of differential equations, linear algebra, and physics. State is defined as a mode or condition of being. By a state space approach, one means a description of a system in which the state gives a complex description of the system at a given time. It implies that there are orderly rules for the transition from one state to another. State. The state of a system, which is a set of variables along with current time, summarizes the current configuration of the system. State variables. In a dynamic system, the state of a system is characterized by a collection of minimum set variables called state variables. Given the input, they must be specified at any time in order to uniquely predict the behavior of the system for t is greater than t naught. State space. The n-dimensional space defined by the state variables as coordinate is called the state space. State vector. If there are n variables x1, x2, x3 up to xn to describe the state, then the vector x of n components is called state vector. This vector is denoted in matrix form as x is equal to x1, x2, x3, x4 up to xn matrix. Here is a representation. State space representation. State space representation of a given system consists of two equations. They are state equation and output equation. Both the above equations must be represented as function of state variables and input. State model of linear system. In general, when we represent a system of state variables, we do so by a set of first order linear differential equation of the form x1 of t, that is the first derivative, that is equal to a11 x1 of t plus a12 x2 of t. It goes on a1n xn of t plus b1 u of t. Then x2 dot of t is equal to a21 x1 of t plus a22 x2 of t plus it goes on a2n xn of t plus b2 u of t, and it goes on. Then xn dot of t is equal to an1 x1 of t plus an2 x2 of t plus it goes on plus ann xn of t plus bn u of t, where x1 of t, x2 of t up to xn of t are state variables. The output of the system can be expressed as a linear combination of state variables. That is, y of t is equal to c1 x1 of t plus c2 x2 of t, and it goes on cn xn of t. The above equations can be written compactly as x dot of t, that is equal to ax of t plus bu of t, and y of t is equal to cx of t plus du of t, where x of t is n cross 1 state vector, u of t is m cross 1 input vector or forcing function, capital A is n cross n system matrix or coefficient matrix. This is the representation of x of t, that is n cross 1 state vector, n rows 1 column, and A is n cross n system matrix, that is A11, A12, and it goes on A1n. Similarly, A21, A22 goes on A2n, and AN1 it goes on up to ANN. The B matrix is equal to B1, B2, and it goes on Bn, and C matrix is equal to C1, C2, it goes on Cn. The relationship between the state equation and transfer function. Now consider the equation x dot of t is equal to ax of t plus bu of t, and y of t is equal to cx of t. Assume zero initial conditions and take the Laplace transform equation. We get Sx of s is equal to Ax of s plus Bu of s. This is the Laplace transform of x dot of t equation, and y of s is equal to Cx of s. This is the Laplace transform of y of t equation. So given the equation numbers as 1 and 2, and s minus a x of s is equal to b u of s. Multiply s with identity matrix and rearrange the above equation. We get x of s is equal to 1 divided by si minus a into u of s. Consider this as equation 3. Substitute equation 3 in equation 2. We get y of s is equal to c into 1 divided by si minus a u of s. The transfer function is y of s by u of s, that is equal to c into si minus a the inverse into b. Consider this as equation 4. Therefore, c into si minus a inverse into b is the transfer function of a system whose output is y of s and input is u of s. Note, the d is taken as 0 because all physical systems are low pass filter. For low pass filter, the value of d is equal to 0. Solved problems in state space analysis. Obtain the transfer function of the system defined by the following state equations. This is the given equation. x1 dot x2 dot matrix is equal to minus 2 minus 1 1 minus 2 matrix into x1 x2 matrix plus 1 0 matrix u. The output y is equal to 0 1 matrix into x1 x2 matrix. For this equation, we have to determine the transfer function. Solution. The transfer function is y of s by u of s. The formula for calculating the transfer function y of s by u of s is equal to c into si minus a inverse into b. In the given problem, the C matrix is given, A matrix is given, B matrix is given. That has been taken and substituted here. So the transfer function is equal to, the C matrix value is 0 1 matrix and B matrix value is 1 0, and in the problem they have given the A matrix. Now we have to calculate the value of the Si minus A. I is the identity matrix. Here 2 by 2 value is given for A value. So we have to consider the 2 by 2 identity matrix I. So S into 1 0 0 1 identity matrix minus 2 1 1 minus 2. This is the A matrix value. So if you simplify, this means we get S plus 2 1 1 S plus 2, and the transfer function is equal to matrix C 0 1 into Si minus A matrix is S plus 2 1 1 S plus 2, the inverse, into 1 0. We have to determine the value of the Si minus A, the inverse. Formula for calculating the Si minus A inverse is equal to Si minus A, that is adjoint of Si minus A divided by determinant of Si minus A. So after calculating the value of Si minus A inverse, the value is, transfer function is equal to 0 1 into 1 divided by S plus 2 the whole square minus 1. This is the determinant value, determinant of Si minus A value, and Si minus A, that is the adjoint value, is S plus 2 1 1 S plus 2, and the B value is 1 0 matrix. Now the transfer function is equal to matrix 0 1 into 1 divided by S square plus 4S plus 3 into matrix S plus 2 1. So simplifying, this means we get 0 1 matrix into S plus 2 by S square plus 4S plus 3 and 1 divided by S square plus 4S plus 3. If you further simplify this equation, means we get the final value as 1 divided by S square plus 4S plus 3. This is the required transfer function. The transfer function y of s by u of s for the given state equation is 1 divided by S square plus 4S plus 3.
Thank you very much for listening this lecture. For further updates, kindly subscribe this channel. If you like this video, means kindly share this video to your friends. Thank you.